Group 5, Doctor.
Okay, sure. You may share the screen.
Okay. Can you see? Can you see the slide?
Yes, yes, sure.
Okay. Good evening, everyone. We are Group 5, and our topic about the real-time autonomous vehicle prototypic development. And the first part is about the objective and scope. And we want to develop a functional prototype of an autonomous vehicle capable of real-time lane detection and obstacle avoidance. And the scope highlights we want to build a real-time lane keeping and obstacle detection and emergency stop and the automatic failover. And the bonus point about the autonomous routing and navigating around a blocked line and resume course. That's about the timeline. We use the Gantt style and the deliverables. We only have the 6 phases about the requirement planning, design, SIS, SDD, and hardware coding, building, and testing, and demo, and about the final. The deliverable is about the SIS, SDD, STD, and then leave them the next people. Yeah.
Our system consists of 3 core modules: line management, obstacle avoidance, and rotary routing. The camera handles line detection. If it fails, the IR sensors takes over. Obstacle avoidance is managed by camera and ultrasonic sensors. If both fail, the system performs an emergency stop. Next. For non-functional requirements, it responds in under 50 milliseconds in 95% of cases, recovers within 100 milliseconds, dashboard updates in less than 100 milliseconds, and touch response under 150. It supports multi-protocol communication, legacy modules, and comply with ISO and GDPR regulations. Next.
Okay, our system is a hybrid architecture combining a 3-layer design. The hardware abstraction layer runs on Arduino to handle real-time control, while the console layer and the behavior layer run Raspberry Pi for decision making and task execution. Next, the FSM enables safe and deterministic decisions like switching from camera to IR tracking or entering rerouting. In real operation, the green LED indicates camera mode, blue shows IR fallback, and red signals a stop due to obstacles. The system recovers autonomously and gives clear feedback and through LEDs and buzzer. Okay, next.
Okay, it's my part. Next. Okay, our system is built entirely on Android Uno and deploying board, which handles all sensors reading and motor control in real time. We use IR sensors for line detection and ultrasonic sensors for obstacle detection, and the L298N motor drivers control movement, and the LEDs and the buzzers provide the visual and audio feedback. And this, the GPIO pin mapping is clear. For example, GPIO 5 is connected to the LED, and the GPIO 17 is connected to the live IR sensor. Next. The flavor logic is simple. If the IR sensor detects the line and continue to driving, if no line is detected or an obstacle is too close, stop driving and sun alarm with the red LED and buzzer. And this setup is low cost, reliable, and well suited for real-time response for Arduino. Okay, next.
Yeah, let me include the software implementation part of our vehicle system. First, we run a real-time control loop at 10 Hz. Every 100 milliseconds, the system reads sensor data from the camera, IR, and ultrasonic modules. It then updates the finite state machine, calculates the control output using PID logic, and sends commands to the modules. Finally, it logs data and updates the indicators like LEDs and buzzers. On the right, you can see our task sharing priority table. The highest priority is given to sensor interrupters. For example, ultrasonic echo detection. The FSM and control updates run as pretty text. Stressor indicators and logging are lower priority background tasks. This can ensure real-time responsiveness while keeping the system scalable. Next. Let's talk about the key algorithms and data structures. We use the PID controller to center the system within the lane. The controller calculates the error between the design and actual center of the line and adjusts the motor speeds accordingly. Next. In the table, our obstructure decision threshold is set to 50 centimeters. If an object is closer than this, the FSM triggers a sharp and rerouting action. Next. We also use the event dispense architecture, aka EDA, or events such as sensor triggers or time ticks are pushed into an event queue. The FSM pops these events one by one and reports accordingly. This makes the system modular and improves timing reliability. Okay.
About our project testing methodology, the code strategy is about adopt a scenario-based black box testing approach, verify the input-output behavior of the system, and all tests were conducted on this platform. To achieve safe, repeatable fault injection and logical verification. Next. And the figure shows the defect life cycle. Ensures the systematic tracking and resolution of issues, and there the entry and exit criteria showing all the tests are done. Next. And this table summarizes the code test scenarios designed to verify all the key functions of the system. The normal options,
Sorry, your voice is not clear. Can you repeat for this table?
Yeah, okay. This table summarizes the code test scenarios designed to verify all the key functions of the system. And the scenarios are the
I cannot hear your voice. It's slowing down the voice right now.
Sorry, I try to. How about now?
Sure. Good.
The table summarizes the code test scenarios designed to verify all the key functions of the system. The scenarios are in the tables are the camera failures, component failures, and camera obstruct and the reroute. And next. And all two scenarios have the test essentially have the key requirements as us. And
I think it's not clear now.
Yes, voice not clear.
Yes.
I think you should stay close to the microphone. I think you are moving.
I have it, now.
Okay.
And the test successfully verified the normal time sensor for speaking obstruct detection and stop. As well as the path replanning logic in two models. Next. And that's all.
Sorry, can you repeat back for the table? Just now your voice is not clear, so I cannot catch up for the table. Can you repeat in short?
This table?
Yes, because your mic is missing somehow just now. Maybe your group member can help.
Sorry, those are maybe my mic has some problem.
Hello, hi. Yes, doctor. I'll chip in from here.
Okay, carry on.
Okay. Yeah. So 5 core scenarios, right? So the earlier table, what we were trying to explain is we have a few simulations that we did. So we're trying to have the scenarios implemented in the simulation to test the logic how it actually works. So that in case if there's any failure, we can actually find out earlier, and we can also test the logic that we're actually going to implement in the actual prototype. So this is the test results. Like yeah, this is just like how to say just an assumption. So the next slide will actually explain further. Yeah, so we actually use Walkui. So Walkui is one of the simulation platform, but the limitation is that we can't actually implement camera and IR sensor. So for simulation, we actually assume that the camera is working fine, because even if we're going to implement camera, so camera actually uses object detection model. So it's actually we don't want to test that logic. We want to test more towards the movement logic. And the IR sensor, since they don't have IR sensor, we actually would just test the object detection. So whether the model can actually detect object, and if it detects, how is it going to respond to that that object, and also how if a camera is failure, how is it going to actually work from there? So yeah, so I'll share my screen for the simulation.
Okay.
Can you guys see my screen?
Yes.
Yes.
Okay, yep. So this is the diagram how we actually drew the simulation. Like so we assume there's like 4 motors and then there's like 3 ultrasonic sensors. Since we can't actually do the simulation of the robot moving and everything, the vehicle moving and everything, so we just want to test the logic. So we have 3 buttons here: the camera failure button, obstacle button, and camera plus obstacle. So and we have the LED to actually light up to notify us like what happens if there's a camera failure, how is it going to respond. So the first scenario is assuming the camera is working fine, how is the model actually working? So from the terminal we can actually see that okay, so everything's working fine and it's like moving forward, and the green LED is actually lighting up. And second scenario will be like if the camera fails, what's going to happen? So usually, like based on the scenarios given, like you should use IR sensor, but since we don't have IR sensor, we use ultrasonic sensor. So we press the button and we can see second scenario how it's actually working logic. So that's the logic, the code logic, how it's actually responding to each condition. And then the third scenario is, let's say there's an obstacle, how is it going to respond to that? So then you can see the light changes, So the LED light is actually more of a responding variable. So it actually gives us like an indication of how what's working. So the LED is more towards like a fail-safe kind of thing. So if the logic's working, the LED should light up so that this logic is actually working. And the last, let's say there's camera fail and then there's obstacle in front. One more thing is, let's say if the obstacle is there, then we leave the obstacle, but then if the camera is working fine, it goes back to the same logic where it continues moving forward using the default function. So last is camera plus obstacle. So we can see here, like if there's an object and
your mic got problem.
Lagging.
Mm.
Can you guys hear now?
Yes. So maybe you can repeat for the previous part.
Okay, so let's say if this camera's not working in this obstacle, so it tends to use the obstacle. So you can see the terminal where like the scenario 3 or scenario 4 actually you kick it. Yeah, so that is actually like it's trying to reroute itself using the ultrasonic sensor if the camera fails and there's an object in front. So this is like how we test the logic, how the entire, like if let's say we have a Raspberry Pi and we want to test a prototype, before we test a prototype, we can actually test the entire logic. If you have 4 motors with ultrasonic sensor, how it's going to move, and it's an object, how is it going to re-navigate? There's camera failure, how is it going to work? So we test the logic of the program, and then we can implement it in prototype. Yep, so that's all for presentation. Any questions?
Okay, you can first.
Oh, okay, I have a question. This is Xuanyu, and I want to know how you can realize or meet the non-functional requirements, for example, like the real-time responsiveness and safety, like this. How do you meet and realize?
Okay. Okay. So let's say it's camera. Sorry.
You first.
Yeah. So let's say it's camera failure, right? We press the button to actually mimic the real-time response for it. So when there's a real-time response, means that it's like how is it responding to an actual effect, actual like, object in front, and how is it actually working towards it, like reacting towards it. So that's why we actually use this camera failure, obstacle, and cam plus obstacle. So these buttons are the ones that's actually mimicking the real scenarios. So how it responds to it is the real-time logic. Do you understand?
Yeah, thank you.
Okay. Yeah.
And I have a little addition for this question.
Okay.
Okay, well, so in our SIS document, we clearly define the real-time responses as a non-functional requirement, and like specifying like control decisions must be updated every 100 millimeters, like safety addressed by stating failover behavior, and if, for example, if the sensor fails, the system must be able to switch to backup or stop safely, and these are later validated in the STD and implement through the FSM logic in the STD. So in our report line. Okay, thank you for your question.
Can I ask a question? Very simple question. Because I mentioned that your design, your group design also have the same ways as also have IR sensor and the ultrasonic sensor. So I want to know what kind of priority policy you may decide on it. Because for example, like which sensor is more important to directly depends the stop instruction comment.
Okay, so we can't test IR sensor in Walkry, and we can't test the camera sensor here as well. So camera means it more towards object detection model, right? So the camera is actually working, you detect objects, and you can actually, the entire thing is a different algorithm. But we assume that camera is working and IR sensor is working. But in case both of it fails, how is it going to respond? That's where we have ultrasonic sensor, and we can simulate this here. So let's say both of it fails. And using ultrasonic sensor, can it still navigate or not? So that's like the fail-safe method. So you try to simulate that, and if ultrasonic sensor is working, then it's going to use that. But say if it doesn't need ultrasonic sensor, it's going to go back to scenario one, where it uses camera to actually move forward. So default will be using camera.
Okay. So your policy is like to use the ultrasonic sensor first and use the IR sensor later. Is this your priority policy?
No, camera sensor first. Cameras first.
Sensor first.
Yeah.
Yeah. Okay. Okay.
Yeah.
Thank you.
Okay, here is Miyoshi. Maybe I have a little small question. So, why do you use Event-Q architecture?
Yes, the Event-Q can decompose the hardware, eventuals, and control logic. It ensures that all sensor inputs and timers are processed in order, and prompting risk predictions and make the FSM more reliable.
Okay, thank you for
Okay,
your
thank
answer.
you. Thank you, President.
Okay, I have a question for this group. Any limitation if, let's say, you can do the software and also hardware if you have the hardware component and so on? Is there any limitation in this project, especially for the setup and so on?
Yeah, the setup, it doesn't have
Or any weakness that you want to improve in future, especially for your software coding or function?
it will be like more like error handling. So when Dr. actually asked the error handling, I just realized that we didn't actually implement that. So let's say if there's any error, we won't actually see in terminal. So it implemented fail-safe of the sensors, but we didn't, in case if there's anything else that goes wrong, we don't actually have the error handling implemented. So in future, we can actually improve that. Did I answer the question?
Okay. Yes, okay.
And I have an addition, and because we don't actually use the Raspberry Pi in this system. So if we want to compete the software in this operation, so we need to have an operation, right? So we need to based on specific hardware. So let's what we will future maybe to finish it. Okay.
Mm-hmm. So
Thank
for
you.
this project, right? When you do this project, what do you think about this architecture of your device? Is it a software modular, or is it provide the scalable and easy to update your source code?
Sorry, Doctor, I didn't catch your question.
About the
Modular.
architecture, is the software modular, scalable, and is it easy to maintain or update for this through your source code? Is it
Yeah, we
is
use
it easy
layered.
to update? Yeah. Anything
use
if you want to top up.
We use layered architecture, but we didn't implement modular. So if modular, it can be like scalable further, but we just use layered. So we just want to test the implementation only.
Okay, good.
I think in the simulation and the Wima also I have a show later. We in our document we have a right that we adopt the modular design in both hardware and software. Like each sensor and control logic is separated into the logical models. So I think it shows that it allows to easier debugging, upgrading, and maintenance. So I think each part is separated of concerns. So it's upgrade maybe more easier to us.
Okay, so how about the latency? What's the end-to-end system delay from sensor to the car steering? Do you have any idea for this project? For the latency?
No, doctor. We didn't test that. We didn't test
Okay.
that too much. Yeah.
All right. Okay. Thank you so much for this group. Well done. Can we proceed to next group after 15-minute breaks? So we'll be back later at